then I'll start. Hi, everybody. I'm Anna Kuklewicz, and I'll do self-presentation. I'm currently a postdoc at Max Planck Institute with Bernd Schele, and I've graduated previous year from there, also with Bernd, complete my PhD. Yes, and today I'll present our recent work, ReFAM, attention magnets for zero-shot referral segmentation, together with Enis, that we've done together with Enis, PhD student at ATH, and folks from Google, Alessio, Frajat, and Federico, and my MBA colleagues as Jan and Bernd. So, first of all, we're talking about here zero-shot referral segmentation. It partially was already covered in the previous discussions. So what is a task? For example, imagine we have an image or a video with multiple different objects, and we have an expression. In this case, it's largest orange goldfish. And we can see here that there is many different goldfish, and you can imagine that maybe not only orange, but different fish. But the point is to find the largest orange goldfish. So we need to also account to the attributes and find the particular object in this case. So we need a segment, produce a segmentation mask for this particular object. And in videos, it might be even more complex tasks. More object can appear or disappear. So, so it's very large, interesting work in the future. However, we here limit ourselves to more simple setup as a one frame or an image. So what was done in previous work, in this case, it's zero-shot, and there is not so much work in this domain as the task is very complex. And all previous work rely on, for example, creating some mask proposals with segmentation models, or training models, creating local and global reasoning modules that take into account some attributes. And then one of the main parts is utilizing CLIP visual language space, where these proposals are ranked and then filtered out based on this ranking and keeping, for example, the best pairs. So in our work, we actually having very different direction. We basically don't rely on any of these components and rely on diffusion models. Why diffusion models? So essentially, they are huge models which are pre-trained on a lot of pair data, and they able to generate detailed images like corresponding to the given semantic in the sentences. So it's already should capture semantic information there, maybe not explicitly, but implicitly. So when we're hoping on extracting this information from diffusion models, and therefore we propose very simple pipeline. We're having an image and the corresponding referral expression. So we have some pre-processing steps as a variation load encoder to encode image into the latent space, language model to encode text in the latent space, and then DAT. It is a diffusion transformer. It has a lot of blocks containing cross-model attention and individual attentions for individual modality attentions for images and text. So there's a lot of communication between the modalities, interplay, and we extracting our attention maps from different blocks from diffusion transformers, cross attention maps. So for example, here we can see 4 attention maps where each attention map, visual attention map, correspond to each textual token. Then we apply softmax across these text attentions, do some filtering on the top. I'll go later here. And we do, for example, averaging and find arg maximum, which corresponds to the main response to our referral expression in the attention maps. Giving this arg max point, basically to have a refined segmentation mask, we apply some model to basically do infer based on 1 point prompt infer segmentation mask. So the most interesting part here is what and how we filter the attention maps with respect to the text tokens. First, I would like to mention why we actually looking at the attention maps and how they are already used in diffusion models. So they're already widely used, and they're like in the ongoing research or on exploring the properties of attention maps. For example, in this work, the authors created synthetic images and with a respective segmentation mask. So due to the difficulties of creating such data sets in the real world, they approach it from synthetic point of view. And for example, based on some thresholding of the attention maps, they found very high quality, good attention maps, which basically producing segmentation. On another domain, also attention maps highly used in image editing when, for example, you need to change the color of this dress to the black one. It also, all of the works rely in some regard on the attention maps and manipulations with them. And recently there was concept localization paper, which essentially pointing out the different concepts also in the attention maps. And which actually very similar to referral segmentation. However, this work has a lot of limitations. So if you can see here, all the given concepts should cover the whole scene. And for example, the authors in this work, they evaluate on segmentation tasks. However, apart from only segmenting, for example, a dragon, they also manually provide all other concepts which appear in the scene potentially. So for example, here will be dragon, rock, sun, and clouds. And if you sum everything, then it will cover the whole attention, the whole image uniformly. So this was a limitation. Also, concepts are very simple, one token words. So they don't extend to larger, more complex sentences as in referral expressions. And it should be simple images with easy identifiable concepts. So going further from here, we first making a step forward to understanding how the information, semantic information emerges in DATs. So here we have referral expression white cow with brown patches. So this is the image. On the top, we have text-to-text attention. So all tokens from this referral expression, a white cow with brown patches, with respect to also text tokens, the same text tokens in transformer blocks. So, and on the bottom, we have text-to-image attention. So all image information, like the cow, with respect to only one text token, in this case, patches token. And the x-axis is basically DAT consists of a lot of blocks. And from on the left, we have the beginning of DAT, like starting when the only tokens enter the DAT. And to the right, we have the last layers of DATs and attention. So what have we observed here? Interestingly, that in the beginning, in early layers, there is no usable information. So this is already a pre-trained model. We already take pre-trained diffusion transformers and diffusion models and abstract features from there. And we observe that there is no usable information. All attention maps are uniform, both image and text-to-text attentions. And mid and late layers, we have sharpened semantic alignment. You can see here, for example, in the last layers, we have particular exact patches in the cow with respect to the patch tokens. Also, what we found interesting is that this emergence of this like columns, which are very bright, and we call them global attention sinks. So what are the attention sinks is already exists. So it's very recent findings in first in NLP and then in vision. So you might heard about them as massive activations or, for example, registers in the vision. They're all the same. They share the same properties. For example, that they very high norm values of these tokens. They have very limited information, and it's always very few tokens that appear. For example, here on this figure, you can see this red column, very similar to what you observed on my previous slide. So it's the first token which accumulates all the attention, and this was the first work, efficient streaming language models with attention sinks, that discovered this phenomena. And basically they utilize this for streaming methods, but it's essentially observed in all LLMs. So like, for example, registers as well, you can see here these bright spots that also would be attention sinks because they accumulate a lot of attention. So far, we observed that there's only, for example, in text-to-text or vision-to-vision. And what's interesting in our work, we observe is like cross-model attention sinks. To be more specific, for example, on the left, we have text-to-text attention, and we have here that the first token, this underscore, is essentially attention thing with respect to text as all other text tokens. At the same time, we observe that it's also attention thing to all visual tokens. So you can see here, the first attention map is uniformly high values, and whereas the rest are not attention things. What we also observe that like position here, it's not always like first token, it changes the position all the time in diffusion models. Like, and it's different from LLMs because they are quite defined that it's most likely it's a first token. And here it's jumping around. And for example, here it's on the second token. And you can see here, if you look at the visual, the token is actually camel. So, and if we, for referral expression, if we're interested in the camel, then it's basically make our information wrong because it allocates on the meaningful tokens. So to basically summarize what we observe about this attention sinks, like global attention sink, how we call them. So they first of all have an informative role, similar to what was observed in previous works. We performed some experiments and shows that removing them doesn't harm the performance. We also observe empirically that they are indicators of semantic structure. They not appearing in the beginning of the layers, in the early layers of diffusion transformers. However, they appear later in the layers where semantic structure appears in the visual space as well. And as we saw on the previous slide, they have a potential harmful role when they're allocated on meaningful tokens. So we observe that majority of gas tokens corresponds to stop words, which are meaningless tokens. And however, more than 20% of this token attention sinks, they fall on meaningful tokens, which may be harmful for their performance for the referral segmentation. So in this case, we observe and propose some redistribution strategy. So we basically have our referral expression and append more stop words that we call attention magnets. What are the stop words? It's words with little semantic information, such as there, is, at, which, and so on. And it's very common that they're just filtered out in the NLP community for the preprocessing of the sentences, for understanding of their information there. So what we actually do here, we just take our referral expression, append the stop words for the preprocessing, and then when we extract attention maps with respect to all of them, and when we do during filtering, we just filter them out. So this basically allows us to redistribute attention, which I will show later, to the stop words, and basically get rid of this background information and reduce reliance on some predefined words in the scene. So we filter attention magnets and other stop words, and we apply again argmax, and we getting the segmentation with the SAM model. What we observe here, so by adding this additional stop words, attention magnets, we redistribute attention sinks to them with more than like 10% more now gas tokens on the stop words. And we also observe that the attention maps, if you can see here on the left, this is without our attention magnets, they are becoming much more clear and much sharper attention maps, which is a very desired property for our task. So why we're actually having stop words? Because we observed that there are natural garble collections and LLMs. It also was mentioned in some works. It was not stated very clearly, but in some cases, it's LLMs actually allocates this attention sinks to the stop words, and we observe similar behavior. So it allocates a surplus of attention there. What we also observe that they are attending to the background because these stop words appear in all the sentences when the model is trained, and the model learns that it can basically allocate their attention there, which are not described in the sentences. So here we propose, we make some ablations. Is the choice of stop words is actually important. So we actually sample different stop words. We experimented also with the most common and the least common stop words, and we observed that basically essentially using stop words is important. However, using just random vectors, it also helps to redistribute attention. However, it's not as efficient as stop words, which model was using every time during training. What we show here, here is its state-of-the-art performance with respect to 6 other data sets on image referral object segmentation and referral video segmentation. And we show that we are actually, with this approach, we're performing the best across all the data sets and across all the models. What was interesting as well, so our attention magnets redistribution strategy helps in all the cases. In referral expression segmentation, there is very common tricks which are in the communities done. For example, you have the whole referral expression, and as we observed a lot, that these models are usually biased towards nouns, and using some NLP library, we can basically filter out everything but the main object as a noun phrase. And here we show, for example, if we use this trick as well, it also boosts the performance. However, appending at the addition of our attention magnets, it helps the performance even further. Another trick, which is also standard and usually done, is basically adding special bias. We detect essentially special words, for example, left, right, top or bottom, and adding special attention, additional bias in the attention based on this information, which basically shifts our focus towards left or right, for example. And we also observe that it also helps. So all this basically filtering, additional filtering, and attention navigation biasing helps. However, our attention magnets helps all the time boost performance quite significantly by about 10%. So to conclude, we propose our refine framework for zero-shot referral segmentation based on diffusion transformers, and we made additional step forward in understanding semantic in diffusion models through the lens of LLMs and attention sinks. And based on this, we propose attention redistribution strategy with attention magnets, and we achieve state-of-the-art results on zero-shot image and video referral segmentation. Thank you very much for your attention.
Thanks a lot for the presentation. Very nicely timed and also very interesting work. I have a few questions, but if anyone else has any question, please jump in before me. Otherwise, I can also ask a few questions. I guess the question for me is, it's very curious phenomenon that you have these attention sinks. I've seen them in other settings. You express them as kind of garbage collector for any redundant attention.
Mm-hmm.
Does that interpretation lead to, so conceptually it's not kind of working in my head how this kind of role is making better kind of segmentation possible. So I wonder if you have any explanation of the mechanism, how the how those sinks, attention sinks, are actually helping with the segmentation of the object, like delineating the edge of the object and so on.
So in this case, we have two parts actually. So it's attention sinks, which essentially sometimes contaminate these meaningful words. And in this case, basically redistributing attention sinks from meaningful words to this additional basically allocated to stop words. This helps in terms of overall because we do this filtering afterwards, right? We always do some filtering on this referral expression to detect the phrase which we want to keep in our sentence, which tokens we want to keep. And if we keep tokens which have this attention things, it's basically meaningless, and it will be the same, similar to just randomly sample in the uniformly sample from the image. So in this case, this was first part. And second part, it's not related to the attention things, but rather just having this additional allocations in the form of stop words basically helps to redistribute background to them. And because like our intuition there is that the stop words just was appearing in every sentence, in every time when the model is learning something. And it's just easy for the model to know, okay, this is meaningless token, and whatever is not related to the semantics of this sentence, we can allocate there instead of somehow redistributing among these other words which are meaningful. And for example, yeah, this was the two parts here.
I wish to understand better, like the causal link between the sync tokens and the yeah, segmentation perfectness, right? So I think you had a ablation study where you show the effect of introducing the sync tokens. Can I take a look at that again? I see.
This one.
Right. Is there also kind of a continuous version of this where you kind of slowly introduce the sync tokens? And
so we essentially, of course, we did these ablations, but right now in the paper, I think it's lacking this particular ablation. So it's indeed, so in terms of, are you interested in the performance? Because here the performance, so even 1% of this GNF performance is quite huge, because it's basically also includes, so this segmentation with respect to boundaries and the overall segmentation. And it's also overall very much dependent on their SAM performance. It also has a lot of drawbacks in terms of mis-segmentation. It's not perfect, not at all. It's far from perfect of having a segmentation. And also the point is that we have only 1 point of like sampling or prompting sum. This is also makes it's not as robust as it's possible to do. I'm like quite confident that like in the future it would be possible to make it more robust by prompting a bit of more points instead of only 1 argmax, because it already gives very good segmentation mask overall. So when we could just refine it with the SAM model, but here we just basically was proposing very simple pipeline, which is already was showing very good results comparing to all other methods. So we stick to this. But overall, so we observed, so like this additional attention magnets, if introducing, if we have 1 attention magnet, for example, it doesn't work very well. So for example, from 2-3 attention magnets additional, it's already starting performing well. And if we add even more, for example, up to 20, so it's already also increase bit by bit. So, but there it
Really? Okay.
saturates. Yes.
So it saturates and never decreases.
Yeah.
Oh, wow.
So
Okay.
it's and but yeah, so far, but like I would need to run additional experiments on this. So I could show you. So essentially here I have, for example, this figure, and if you can see this, basically all this this blue boxes on the bottom here, it's our this additional stop words, attention magnets, and you can see that as a background, all the small details, it's managed to allocate into each of these additional stop words. It's allocating this small detail. So if we have adding more of them, it basically would then just separate maybe these two sticks in the background into two sticks instead of one stick, and also maybe more detailed leaves in the background again. So it basically will be having more more clusters to allocate each concept which it sees in the background.
Oh, this is super, super interesting. So I have a lot of questions here, but maybe the most important ones are, so what prevents you from adding lots and lots of stop words? Is it a computational issue or something else?
No, nothing. It was already performing good, so we kind of we needed to conclude this work at some moment, and I think there were so many things to do from different directions.
Like
There is so many.
Okay.
Yes, it's there is no computational constraints at this moment because it's like I think LLMs are able to process like really long sentences. I think we have not reached the moment where you would stop, but I think it just like won't need so much. I think depending on the complexity of the sentence, and again, here it's still very simple sentences as we were seeing before, like in previous presentations, you need some semantic reasoning if, for example, negations or more complex referral expressions, I think they're not yet captured so well with this framework. You need more playing around with the sentences and the attention maps, which to choose and how to choose the things, and maybe also by appending another attention magnets which reallocate some different kind of attentions there might help there. But there are so many things still to do, and there's so many directions.
Yeah, super interesting. Okay, thanks. I think the time is up for now, so I'll keep the other questions for later.
Okay, thank you so much.
Thank you so much. And Sagar has joined. So welcome, Sagar, to the session.
Hello, can you guys hear me?
Yes, I hear you.
Yeah.
And I see you.
Yep. Sharing my screen. So unfortunately, I don't have presentation slides, so I'll be presenting directly from the paper.
Yeah, which is fine.
Okay.
Yep. And you have a company, right?
Yes. So this work is something that we did as a part of our research at JoySpace AI. At JoySpace, we have multiple products, but our research is basically around multimodal AI systems, figuring out how LLMs and how generative AI can help people write personalized messages, personalized stories. For us, when I say stories, for the context of this paper, it is image and text as only two modalities being considered. But at JavaSpace, we consider audio, video, and other signals of the system as multiple modalities as well. So, talking about the paper, this paper takes authors, their writing style, their stories, and tries to find if it is possible for AI systems to generate a visual representation of author's writing style. Okay. This problem falls in the area of computational storytelling. I did my master's in computational storytelling. I wrote entire thesis on it using probabilistic methods. At that time, it was very difficult to generate a cohesive story. But now LLMs have paved a path for writing a cohesive story. So we are going a step further and not limiting ourselves to only the textual story, but assuming author has already written multiple stories, can we represent author's style in terms of images? There are numerous applications for this. For example, adding visual cues to the stories, writing or generating stories for children. Creative arts is one of the category that falls under the area of computational storytelling. For this particular paper, we are concerned about stories that we scraped from Reddit. So Reddit has one of the subreddit is storytelling specifically. We scraped data from 49 different authors who posted stories on Reddit. Then we created author writing style, kind of evaluating their writing on 4 particular pillars of storytelling. How good is their story? What exactly is usually their plot? How good is their creativity, etc. I'll explain this a little bit in detail, down the line. And then we used an LLM to generate a prompt for a diffusion model, and diffusion model generated images. Then to evaluate these images, we use a sample of people that work for our company and few of our customers as well. And we gave them these author writing styles and images and asked them, hey, what do you think? Does this image represent this story, or does this image represent this particular author? And that's basically the entire paper. I can take questions as I speak as well. So if anyone feels like asking anything, we don't need to really wait till the end. You can ask me at any point in time.
I guess what I'm most curious about is some examples of
Oh,
how
yeah.
different styles result in different images.
Yes, I have a couple of examples in the paper. I did not prepare slides because somehow I got an email a few days back that the session is cancelled. So I'm like completely unprepared for the session. That's why I joined a little bit late as well. I don't know what happened. So before going to the examples directly, I would kind of phrase what exactly did we do in this particular paper. So we asked these 4 research questions. We were able to answer first 3 of them quite well, I think. But the 4th one is not as well answered because evaluation is really difficult. So the first research question was, can we abstract out the author's writing style and represent it visually? The second research question was, can LLM be consistent about doing this? When we did this research, the measure models that we used is Claude 3.7. We also experimented with OpenAI's 3.5, but that was not as good. So we didn't experiment with a lot of LLMs. We just tested OpenAI 3.5 and Claude 3.7. Claude 3.7 seemed to be working pretty well for our case, so we just continued with that. The third research question that we asked was, is this really a personalization, or is this a generic image that diffusion models are being trained on? Note that we did not tune any research any of the model, not the LLMs, neither the diffusion models. We used off-the-shelf model as it is, and overall research is around, can LLMs understand author's writing style, and can they generate a prompt to visually represent the author's writing style. I have an architecture to explain, but I'll first rather jump to some examples so that we have some understanding of what's really going on. So when I say author writing style, it's a nuanced term. It's proposed by one of University of Maryland students. A few of them have interned at our company, but this was their PhD's work. So their claim was any author's writing style, given the multiple stories, can be represented by what is their usual plot structure, what is their personal element of creativity, what are their usual characters and settings, and how do they use the language. This is really complex. There is no one way of representing author's writing style, but this is pretty recent. The person who interned at our company graduated in the summer of 2025. So this is the cutting edge of representing author's writing style in computational storytelling at this point in time, at the very least. So from these characteristics, we kind of summarized these characteristics for each author, and then we created prompts. So we ourselves prompt LLM to generate a prompt so that a personalized image would be generated for this particular author's writing style. Okay, this is what our prompts look like magical office space, floating paperwork, bureaucratic symbols, etc. And the generated images were like this. And if this is visible, I can drop link to our paper. And this is what diffusion models generated. Overall, we did a questionnaire kind of evaluation. So we had n equal to 10, so it's pretty small eval because few of our employees and few of our customers were the only participant in the eval. And each, I can go from architecture to data to how we evaluate it. So overall, this is the architecture. We scraped Reddit for the stories. We got 49 authors. Each author had at least 3 stories. With their stories, we generated the author writing style based on the algorithm proposed by another paper. We summarized these author writing styles because the way their algorithm is written, it's pretty verbose. There are a lot of duplications as well. So we pre-process the post-process the author writing style. Then we clean and distill the author writing style as well. We gave this to LLM with our system prompt that you are a personalization LLM, and you can write prompts for diffusion models. And user prompt was basically the distilled author writing style. Then it generated 3 prompts for each of the author writing style. Each prompt was given to a diffusion model, which generated 3 distinct images. For the data set, like I mentioned, the number of authors were 49. Each author had at least 3 stories. So overall 147 stories were, I think, more than 147. So at least 3. I think we had around 200 stories or so for author writing style, and this 147 is number of images being generated. For each author writing style, we generate 3 images. Uh, for evaluating this, we had cohort of 10 particular people. We designed the task to ask them specific questions like, how good do you think that this particular, so we first showed them the author writing style, that this particular author likes to write in medieval times. They like to have characters. They like to mix these two particular genres, and they probably think I have something over here. So they like to exploit this particular emotions and social roles. So we gave this information to each of the person who is evaluating the stories. Based on these questions, they answered, based on this information, they answered how good is the match? Does the story writing style really match the image? Then we asked them what specific things were really interesting. Then what was the best image? So we showed them 3 images, and is there any visual distinctiveness? Because one of the things that came across early on is, it does not matter, the author writing style does not matter, no matter what prompt you give. The diffusion model is being trained on particular data set, so diffusion models are going to generate these kind of images nevertheless. So your um, a priori knowledge is not really useful. That's why we added this question later on, that how distinctive are these images? And for that, we showed them 10 other random images generated by diffusion models. I can directly jump to the results. So overall, almost all evaluators felt that author writing style was matching to the images. So average score was 4.1, and this was the distribution. And this scatter plot is something that is more meaningful and more important, is overall style match score as well as visual distinctiveness score. So we got 3.8 as a distinctiveness score, and again 4.1 for author match. So it's the average of what is represented in the bar graph. Overall, we at least partially answered the second and third question. The evaluation is not really strong at this point in time for our paper because of difficulty of finding the participants, and especially because I'm not a university student anymore. As a company, as a CTO of a company, it's very difficult to ask people to participate in a survey that takes around 20 minutes or so. Overall,
I'm sorry. I'm sorry, just have a question. It's rather, do you have more qualitative results in terms of comparing, for example, with different writing styles, but the same image potentially? So it would be really interesting to see what are the outputs and what's actually the influencing, like, for example, how you define that the sentence matches the style. So there's not be one word which reflects, for example, medieval versus, I don't know, current, or like more other styles, right?
yeah,
So
unfortunately, I don't at this point in time. I do have a lot of data from the website that I designed for people to create evaluation, but after this paper, we published it on archive, I took it down, and I was not really prepared for this presentation because I mentioned earlier, I got an email that the session is cancelled. So I thought, okay, maybe it will be rescheduled. If anyone is interested, I can email them or up the website of our eval and send them the link that talks about what exact. So I get what you're saying here. I'm just explaining what are the characteristics of author writing style, but I'm not really showing you what an actual author writing style looks like from an example. And that's probably more interesting. Probably when we submit this paper to some conference, that's kind of a change that I'll consider making to the paper so that it's more clear to people. But at this point in time, I don't have an example of that.
Can I also ask a few questions, maybe?
Yeah, sure. Please go ahead.
So I find this super interesting. I'm a big fan of stories in general, personally.
Mm-hmm.
And I like the fact that you are kind of organizing different styles of authors. And I wonder, yeah, I wonder in general how different the styles can actually be among different authors here.
Oh, okay. So very different. Overall, I can just point to the characteristics right now. So the language use itself. So you see the way we are representing the author writing style, it's based on the first paper that I was cited. I can quickly go to this paper. They have examples in their paper which would be useful in our case as well. They have a huge appendix. Yeah, so let's consider this particular example. So overall, looking at multiple stories, they've come up with this particular plot that author structures story around humorous, light-hearted approach to conflict resolution, which is a pretty abstract concept. If you look at LLMs, even today's GPT-5, this is very, very abstract representation of what authors generally do. Okay, author in terms of creativity, for this particular author, it was author creatively anthropomorphizes animals to reinterpret prompt in whimsical manner. Now, what does this really mean? It could mean thousands of things. That's why our research paper is particularly interesting, that taking this abstract representation of what authors are generally doing, we are trying to represent their style using images. So I don't know if it's making sense more with the example. With the development, what authors usually do, what this particular author usually does is author develops character through their interactions and humorous dialogue, creating vivid and engaging settings. Also, they develop characters through their reactions to satire, highlighting their misunderstandings and cultural differences. So this is what author's writing style looks like. I think this answers Anna's question as well. Like, can I see author's writing style firsthand? What does it look like? This kind of gives at least some idea, if not, I know this could be presented in a much better way, but at least this gives some idea of what author writing style looks like. For their language use, they employ playful and imaginative language to enhance stories' whimsical tone. Now, this could mean 1,000 things. Using the same description, if we ask LLM to write a story, it is probably going to generate the same blob of story no matter what LLM we use. But author's creativity is still represented with these abstract ideas. And we take these ideas and kind of try to generate the images. And with a small evaluation sample, being, it being very small, people do feel that the generated images are representative of what author's writing style looks like. So which we think is a good step forward. The next step for us is to somehow find a large corpus of people who are willing to do these evaluations. If possible, we would also like to scrape more stories from more authors so that we have large sample corpus as well. But we deliberately during this paper, we avoided taking stories which belong to different genre by the same authors. So the stories that we did, we took at least 3 stories from the same author from on that particular subreddit, but there are tags on that subreddit. If any author had stories in different genres altogether, as of now, we have avoided them so that we can get the unified style of the writing and AI not being confused about multiple genres having different plots and different creativity to the stories.
Yep. Thank you so much. Thank you. The time is actually up, so we have to slowly wrap up the meeting today.
Yeah, sure.
So thank you so much again for coming.